Hey physics students, welcome to another edition of Rapid Review for Honors Physics. Today I'm going to talk about applications of things we by now know about energy. I'm going to apply it to the sport of rowing. There is a lot of relationship we can determine between physics classes and various athletic pursuits. Here we'll study the sport of rowing, where athletes pull on an oar to propel their craft forward. So if you were competing on a collegiate team rowing, your coach would be talking to you about how you could best do the motion, right? So pretty roughly the motion is like this, like if this was the oar, and there's a little bit of rotation involved. Let's leave that out. Okay, so the motion is, for the purpose here, we'll just say it's linear, and I move my oar a certain amount of distance against some resistance that's offered by the water. And so you can look at my force times the distance the oar moved, and you can calculate the work that I did, right? Now, the force that I apply is not constant over time. In fact, I might apply more and more force over time up to some peak and then drift off. But if I want to determine how much energy I put in, I can just calculate how much work there was. And this coach says, oh yeah, your total energy, 1/2 mv squared is, which of course relates to speed, is determined by how much work you do, which is the area under this curve. Wow, I just said a lot. Let's break that down, okay? If we look through one image here, you'll see that the axes are the stroke length, that is my position of where my oar is in the demonstration I did for you earlier, and there's how much force I'm applying on the other axis. That's instantaneous force. I say that because my force is varying over the stroke length. Importantly, notice that this graph does not contain time. Often we look at time in our graphs. This one, notice carefully, it's where you are. I would call this position to be a little more specific with our vocabulary, and force, okay? So if you multiply force times distance, you know that you get work. Let's leave theta out for the moment, right? So we're not worrying too much about a cosine theta here. We're just doing a simple force times distance, and we're trying to figure out what happens if the force is not constant. Viewers of this series will know well the slide I am about to show you. If you look at this, you can see my claim that for any force times position graph, force versus position graph, the area under the curve represents the work done by the rower. Okay, this is an integration, this is calculus. That slide comes up in various places, even in the class that, that we're working on here, Honors Physics, which, okay, doesn't use calculus, but you know, right, it's calculus, right? Area under the curve is an integral, okay? So I'm going to make some claims now. The work done by the rower is the area under the curve, as I just claimed, and then I'm going to say it follows from the work energy principle that the work done by the rower is going to be equivalent to the kinetic energy put into the boat, right, once it's moving through the water. I'm going to ignore losses, which is a huge leap, but let's do that for this analysis. And then I can say that the rower can achieve maximum kinetic energy, that is speed, by doing more work. And this is not surprising, right? The more work you can do, the more speed you can get, and that is how you win the race, okay? Let's check out some training. Somebody was training and trying to adjust their stroke profile, and they progressed from this black curve to this red curve, and it might look pretty small, but it turns out that by doing that, this person was able to get more power in every stroke, and I'm sorry, do more work with every stroke, and therefore get more speed out of it, which is the goal. Okay, I will note, if you look at those axes carefully, the left side axis, if you look at it, is in terms of percent of maximum. To be clear, I would rather have had this in newtons, but let's just assume the maximum force is always 1,000 newtons, just so we have it. In fact, if you make that assumption, you can estimate how much work was done by the rower. You can do a graphical analysis of this. I'll leave that to you and see what you get. Exercise 2 coming up is going to be the first of a few more exercises now I'm going to present to you, but I'm not going to give you the answers in this video. I want you to think them through and see if you can work them out. Okay, so exercise 2 is, if you know the energy per stroke, calculate the power output. Remember, energy and power are different if the rower is doing 40 strokes per minute. You'll have to do some conversions of units there between minutes and seconds. Be careful of that. And you should be able to calculate the power output of the rower. You can even apply this to a team of rowers. Take that number, multiply it times 8. I actually changed the pace here. If somebody's doing a competitive pace of 60 strokes per minute, what would you get? What would you get? How much energy total in a particular time, or at what rate is energy delivered, that is, what power can be delivered by a team of 8 rowers. Those are all legitimate questions to be asked. In this exercise here with the light bulb, I ask if it would make sense for our team of 8 rowers to keep the bulb lit. And in order to do that, you need to remember that a watt is a joule per second. And I will remind you, too, that units of energy and power are different from each other. Briefly, energy is joules, from which you can get power if you know the rate. Power might be in watts or kilowatts, or there's others, right? Kilowatt, of course, being 1,000 watts. And if you multiply that power times time, for example, times an hour, you'll get something that looks like kilowatt hours, right? But remember, that puts you back in the energy column. Okay, more on that perhaps in another video. Don't want to get into too much detail on that in this particular presentation. I leave you with one more problem. Your mobile phone, here I show an iPhone 13 mini, and it has a battery capacity given, and from that you can figure out how long it would take our rowers to fully charge the battery. Okay, so not always recommended for rowers to be charging your battery, but if you're in a pinch, maybe you could get them to do it. That's all I have today for work and power of rowing, and our next episode will continue with more on energy and energy conversions. Stay tuned for that.